Hello again, it's Cliff here from Down Under. In this video I'm going to go into Toolsetters, electronic tool setters that automatically set your tool to the software, manual tool setters, dial indicator types and other types, and the old trusty height gauge type manual tool setter. I'll go into them briefly to start with, and hopefully I'll have time to go into it more deeply, help you to sort out what could be the best setup for you. After I've done a quick introduction to the different types, perhaps I'll go through setting up your tool offsets with a mechanical tool setter like this, because it shows the process quite quickly and visually, and then you can see where they all sort of fit together and how they work. And then maybe after that, if I have time, I'll go more deeply into some of the features of the different types of tool setters, or perhaps that will be a part 2 video later on. Cheers. Okay, so let's look at the different options for tool setting, tool length setting. So just a quick overview to start with. You can have a manual tool setter, which is a little spring-loaded surface and a little LED that comes on when it's reaching a critical point, and that becomes your reference point for setting all your tools when the little light comes on. You can have a dial indicator type, so when the needle strikes 0, that's an exact height or surface that you can set all your tools to. Or you can have an automatic electronic tool setter, and PathPilot and probably Mach 3 have a probing routine that brings the tool down onto the top of that electronic tool setter and loads the tool height automatically into the software. Or you can measure your tools off the machine with various devices such as this height gauge, digital height gauge, and you do a manual measurement and load it into the software. So that's a quick overview of 4 different types. There are problems with each one and advantages with each one, and I'll go into those more deeply in a moment. But it would seem on a quick cursory glance that the electronic tool setter is the best option. It's the most sophisticated because the software will automatically do the work for you. There's a downside to an electronic tool setter, an automatic tool setter, because you're bringing your tool down, and that might be an expensive tungsten carbide tool that comes down under a tool length setting probing routine and sets the height into the tool table. But what if something goes wrong? Or what if you did something wrong? You forgot to plug something in or set something, or you've got a fault with the switch inside here, and so the head's coming down and it runs out of travel on your setter and keeps coming. You've got expensive spindle bearings and Z screw, ball screw and nut that could be easily damaged, not to mention your cutter broken and damaged and your tool setter broken. There's a lot of expensive stuff that can go wrong, not just the cost of the replacement parts, but the time involved in rebuilding your vertical screw and ball nut or spindle bearings. And so you want to think carefully, is that the right thing for you? There are ways to reduce the risk with an electronic tool setter. You can have a switch that does the software switching, and then further down, if that doesn't work for some reason, another switch, a backup switch, which connects through to your e-stop system and switches the whole machine off effectively into reset mode. Well, that's a safety precaution, but you could have problems with that, and it means hardwiring in 2 different circuits. And you probably want to leave it set on the table, and you've got coolant spraying everywhere. Is that going to be reliable long term in that environment? So there are concerns with an electronic tool setter. Remember, most of you will only be using your tool setter to set your tool length offsets, the length of your tools. And if you're only using it for your tool length offset and you're using a manual setter, you're just coming down to 0 on the dial, for example, and hitting one button on the software which loads the tool length into the tool tables. That's not a lot of work. Very different thing for a probe when you're setting up your work, there's X, Y and Z in all different shapes, and some very useful probing routines to help you find the position. That will save you a lot of time. An electronic tool setter just used for setting tool length won't really save you much time. You need to be using it in a more advanced situation where you've got a automatic tool changer and different routines for checking tool length, tool wear, and so on. So in order to justify the cost of an electronic tool setter and the added wiring and maintenance issues and risk to your machine, I would say you probably need to be doing quite advanced work so that you can capitalize on the added benefits of being able to do automatic tool length offset probing while it's running automatically from an automatic tool changer, testing for tool condition, whether there's been any breakage, tool wear, and so on. And I would hazard to guess that most people will not be using it for that application and would find it hard to justify over the cost of a simple mechanical tool setter, because you just have that very simple procedure of pushing one button to load the tool length into your tool table. Okay, well, let's do a real world example measuring off the machine and on the machine. So we've set our height gauge to 0. We've put in our test tool and we'll measure the height or the length of it. 74.49 across the flutes. 74.49. Okay, remember that number. Okay, well, now we'll measure that tool on the machine. So we're going to use a mechanical dial indicator type tool setter. So this type you're probably aware of is like a dial indicator upside down with a large surface on it. So first of all, we'll come down and reference we're going to reference the spindle nose on 0 there, and so we'll have tool 0 set and we'll Z0 out. I'll show you on the PathPilot software in a minute. So that's zeroed that. So on the PathPilot side we just set tool 0, come down to the dial indicator 0 and touch 0 there, so we're on Z0. Okay, well, let's touch off the tool itself now. So we'll come down to the same position on the dial indicator setter. So I've called it tool 6. I'll take you through the PathPilot in a minute. Come down. So we're on 0. Just doing it quickly to demonstrate the idea. And I'll take you over to PathPilot and show you this stage over there. Okay, so we've just set our tool on the dial indicator setter of 0, tool number 6. Here we're on the page for the tool offsets, not the probe ETS page, but the offsets, not the work offsets, but the tool offsets. We've got tool number 6 set there, so it's highlighted it here, and we just press on that touch Z button with 0 entered there. Unless you have a shim, then you would enter the thickness of the shim, but we don't have a shim, so we're just going to touch on that. Now if we look across, it'll automatically load the tool length here. Now what was the tool length with the mechanical reading? It was 74.49. so when I touch that off, we'll see whether it's the same via the on machine measuring. Touch that there and we get 74.59. so that's 0.1 of a millimeter error. That's 1/4 error. So you can see that there's quite a big discrepancy between the two different methods. Probably most of the error or the difference will be in the off machine methods of measuring. We already found 2 errors that I discussed, so I would say most of the issue is there. This is probably a more accurate measurement, and we're getting a tool length automatically loaded in of 74.59. So you can see you can very quickly set all your tools just by changing the tool number down here and touching Z each time. It's a quick and probably quite accurate way of doing it. So you can see with this example of off-machine tool length measurement, it's not that accurate, and it's fine for drills or roughing cutters, but if you're doing precision work, you'd need to take a test cut and refine the setting, or do the first part set a little shallow, measure it and make an adjustment in order to do high precision work using a low precision tool length measurement system. Of course, the way TTS operates is that that surface on the flange of the TTS contacts on the underside of the spindle nose, so that you get a repeatable Z position, that it pulls up firmly on the end of the spindle nose in an accurate position. But of course in reality it's not quite that simple. If you have a look, I don't know whether any of you have taken the time to measure it, but you get errors there. I'll just set the camera up on a tripod and show you what I mean. Okay, so we've got 1/100th of a millimeter dial indicator under the flange there, set on 0. You can see it's in contact there, I think. Now if we put the normal tension of the drawbar on there, have a look at the needle. So it's moving up over 2/100ths of a millimeter under normal drawbar tension, and that would be the same with a power drawbar, perhaps even more. So you're getting a movement of your TTS, and that movement is coming from a compression of the TTS flange and a compression of the spindle itself. I'll just show you a breakdown of that. Alright, well I've moved the dial indicator now to the end of the spindle nose. So we know from the last measurement that we're getting just over 2/100ths of a millimeter movement under drawbar tension. That's about a thou. Okay, so now how much of that is spindle compression and how much is TTS flange compression? I'll tighten it up now just on the spindle nose, and it's sort of varying a little bit, but around about 1/100th of a millimeter, perhaps a bit less. So we're getting about 1/100th of a millimeter spindle compression and about just over 1/100th of a millimeter TTS flange compression. So if you have a look at the TTS flange, it's not a very rigid construction. It's a bit like a spring, and this, especially on the automatic tool changer slot versions, it's very hollowed out inside there, and there's a groove in here. It's not a highly rigid design, and so you're going to get some compression. This becomes a bit like a spring washer. So be aware that the TTS system is not a high precision system. So we're getting errors there of about 1 thou or 2.5 of a millimeter. So if you're measuring your tool length off the machine with a separate system, you can see there's an error there of around about a thou, around about 2.5 of a millimeter. Then if you're going to be measuring it with something like a digital height gauge, there's likely to be errors in there as well. I've just put the camera on a tripod again and show you another issue. So if you're measuring your tools off the machine, you'll likely be using something like this, or a hole in your surface plate, and coming down with a digital height gauge. But there's errors there as well. Of course, every system has errors. You know, if I zero this one, for example, there it's zeroed, and I put in a slip gauge. This is a 2-inch slip gauge, so that's 50.8 millimeters exactly. You can see there I'm getting 50.75. So there's 2 thou error there. It's measuring it shorter. So there's 500ths or 2 thou error there. Whatever system you use, there will be errors in your measurement, and there's the error in the compression when it's mounted in the spindle nose. So measuring your tool lengths off the machine is not a highly accurate system. Well, let's look at that again with a finer graduation dial indicator. This is 2 microns, or about 1/10 of a thou graduations. So we'll set it on 0 there. It's loose. Tighten up the drawbar, and you can see you're going up over 2/100ths of a millimeter, or about 2/100ths of a millimeter. That's about 20 microns, or a little bit less than a thou in that situation. So these mechanical dial indicator type tool setters have a lot of advantages. It's a good idea to take your TTS 3/4 inch collet out so that you're clear of the bottom, otherwise you've got to step it only half in. Better to take the collet right out, clean the bottom of the spindle nose, come down to 0. Now there's an additional feature with these. I'll just show you. I'll lift this away. See these little ground buttons? They're grounded an exact height from the base, and you can get a parallel and bridge the gap between them and set your dial indicator on 0. So what that means is that when your dial indicator needle's on 0, those 3 surfaces are all level. And so now we can use those buttons also, for example, for setting your probe and getting the two talking the same language as regards to Z height positions. So setting up the probe to the same Z position language, remember we've just set the tool setter by putting a tool 0 in there and touching it down with the 0 on the dial indicator setter and zeroing the Z DRO. So this is the tool setting position. But if we go, and that's on the offsets page, but if we go to the probe here, the probe setup page, we can set the reference height in the same position with the tool setter and the needle on 0 and Z tool 0 in place. So we just press that button and we've now internally set that. Then we can put the probe in and come down and set the probe length, which is tool 99. Okay, so we know those little buttons are all on a level when the dial is on 0. So we put tool 99 into the PathPilot software. We've gone to the probe setup page and we've clicked the button move and set probe length. And that automatically sets the tool 99 length. I'll just show you that now on the PathPilot page. So remember we had the spindle nose on the dial indicator 0 position, and we pressed this button here, set reference height. Then we've now entered tool 99. We've come over here to set the probe length, and we just click on this little button, move and set probe length. And if we go to the offsets page and look on tool 99, it is measured and installed the length of 102.67. So that's like another milling cutter length or another cutter length. We know that it's a probe, but as far as the software is concerned, it's another length. So now the probe length is relative to the tool length, and they're all relative to each other, so the offsets are all set in the offsets table. Okay, so just recapping, we've just set the probe length into the tool table, tool number 99. So now the probe and all the tools are related to each other in the tool length offsets table. So let's say this is our work. Let's say we've clamped it or we've put it in a vise, and we want to set all the tools to the same surface, the top surface, for example, of our work. Then we just put a probe in, set it on tool number 99, probe Z, set work origin. Now we have got all of the tool lengths which we've measured relating to the top surface of the work. So we've first set the tool offsets, and now we've just set the work offset, and that is on G54, the most normal work offset, but we could have also installed it on G55, 6 and 7 and so on. So for G54, the software knows that that top surface is relative to the length of all the different tools that we've just measured. So you can probably see with this example that this type of dial indicator tool length setter is quite convenient and quick, because we're usually only concerned with setting the Z length of the cutter, the tool height. So we just come down until we're at 0 on the dial, and then just push a button and it loads the tool length into the tool table. So that's fine. So you could argue that you don't really need an electronic tool setter to do that automatically for you, because it's just pushing one button. I would argue that a probe is a much more useful device than an electronic tool setter, because a probe will set you not just Z but X and Y as well, and with different shapes, diameters, squares, internals and externals, there's a lot more work, a lot more time involved in manually setting a position with a Heimer, for example, or a wobbler. But with a probe you can do it very quickly. If you look at a video I did a year or so ago called Probe versus Heimer, I go into the time involved in setting your part up with a Heimer versus a probe, and it's much quicker with a probe, because PathPilot and Mach 3 have all these really useful probing routines to allow you to quickly find, or to allow the software to quickly find, the center or the edge of a block or diameter, inside or outside. So if you're not familiar with a probe, this is the page on the probe page, XYZ probe, probe Z, set work origin. And you can see the advantage of a probe is you have all these probing routines to find corners, internal corners, you can adjust which one and so on. And you have all of these different probing routines to find the inside and the outside of circles and bosses and so on. So that's the advantage of a probe. I can really see the need for that. Less critical to have an electronic tool setter, because it's really only a one button push on the offsets page. On the tool offsets page, you're just pushing this touch Z button and it loads it automatically into your tool offsets table. Okay, so to complete the circle and do the final test, we've set tool number 6 to 74.59 with the dial indicator setter, and we've set the work offset with our probe. So let's just make sure it's correct. So we come down now below the level of the work, push the work in and come up with the tool. And this introduces another way to set your tool offsets. So now I'm pushing in and I'm lifting the tool up with very small steps. And it just goes under at that point. And I'm 3 microns out. So tool number 6 is showing a Z height of 0 within 3 microns. That's within about 1/10 of a thou. So there's probably a bit of luck involved in that, because I set it really quickly while I was making the video, but it completes the circle and shows the system works, and also shows you how you can set your tool heights just with a block of steel or a rolling a dowel underneath. As you lift it up in steps until it just enters, then you can push your tool height for that particular tool and it will load it into the software. So that's the 5th method, which is also practical for certain types of work. So just touching on the surface of the work that we set with the probe, and the Z is 3 microns out. That's very good probably a bit of luck involved. Just looking at those tool setters, so here's the one you've been looking at, this dial indicator type tool setter, and you can see that it's quite cheap, US $29, including shipping to New Zealand. I've pulled it apart and figured out how to put it back together again and done a bit of a study of it, so if I get a chance I'll do a review video of this type of tool setter. Let me know if you're interested. This is the electronic tool setter that allows you to automatically set your software, and I've had a look at that too, and I've got some concerns about the construction and design of this. I even started to design an improved version of it, but I've sort of stopped that after spending a few hours refining the design, because I could see that really there's a limited application for this compared with the dial indicator type, because you're only setting your Z. So please let me know if you can see additional reasons why you would want an electronic tool setter. I know there's a few advanced users that want them for running with their automatic tool changer, doing additional checking procedures, but I would say that's only 1 or 2% of these low-cost CNC machine owners. So please correct me on that if I'm wrong. Thanks for watching that video, guys. If you've got any thoughts on some of the subjects I've covered here, please put them in the comments below. I'm really interested in your experiences with tool setters, and perhaps I can add that in at some stage in the future. Cheers.